everybody, welcome back to the next video of electrostatics. So in this video we are going to talk about the topic known as charge distribution, or we can also rather take it as continuous charge distribution. Now as you all know, charges, they are discrete quantities, but whenever those charges are given into a line or an object having a surface area or a volume, they spread out evenly all throughout the surface or all throughout the line or all throughout the volume of the object. So when that spreading is even all throughout its dimension, so that kind of distribution is known as continuous distribution. So when we are talking about distribution of charges, so we'll be taking that as continuous charge distribution. So by the name itself, there are three types of distributions or three types of charge distributions that we need to know about. Because when you are talking about earthly objects, that is the objects that occur in Earth, are mostly one-dimensional, two-dimensional or three-dimensional. So for each of the dimensions we are going to define three different types of charge distribution, and all of the three types are of continuous nature. So let us first define the first of its type, that is known as the distribution for one-dimensional object. We can take it as a small thing as distribution of one-dimensional object. So in order to understand those kind of distribution, there is a term known as charge density. So since we are going to discuss about three types of distribution, there will be three types of density. So let us first discuss about the very first type, that is known as linear charge density. Linear charge density. So whenever we are having any object, suppose a line or a strand of hair, you can say, having just one dimension, that is its length. Suppose I am having a strand of hair or a particular line or a string whose length is given by L. So if I place some discrete charges in this particular line or in this particular object, suppose if I give an amount of charge Q to this particular line, so this Q would spread evenly all throughout its dimension. Okay, it doesn't happen. So if we give the charge here and if we touch it over here, we do not get an electric shock. That doesn't happen. Or it also doesn't happen that if we give the charge at the topmost part and if we touch at the topmost part, we get a higher electric shock, or if we touch at the bottommost part, we get a lower electric shock. That doesn't happen. Why doesn't it happen? Because whenever you place a charge on an object like such, it will distribute evenly. So any amount or any section of this wire will have the same density of charge all throughout its body. So in this case, we define a charge density that is known as linear charge density. This is denoted by the letter lambda. So lambda is given by charge per unit length. So this will be given by Q by L. Or else if I need to consider a small section of this particular wire, suppose if I consider dl of its length, so obviously in a small section of its wire there would be a small amount of charge, that would be dq. So for a smaller section I can write lambda as dq upon dl. From here I can write down the expression of dq, that would be given by lambda times of dl. In order to get a total q, I can integrate this part. Right? So that is what is known as linear charge density, represented by the letter lambda. So I can either use this formula or I can also go by this formula. What would be the unit for lambda, or what would be the unit for linear charge density? That would be given by, since it is charge per unit length, it would be coulomb per meter, or you can also write it as coulomb into meter inverse. Again, what would be its dimension? So if I need to talk about its dimension, I need to substitute the dimension for each of the individual. So for the dimension of charge is given by A into T. We have already discussed that. So it will be given by A into T, and this is meter inverse, so that would be L inverse, L to the power minus 1. So that would be the dimension for linear charge density. Now let us discuss the next type. So in this case we are going to talk about the next charge density, that is surface charge density. So here we will be talking about charges which are evenly distributed over a surface. So let me just take a surface like such. Okay, and let me place some charges Q over the whole surface. So if these charges are positive nature, that positive nature will spread all throughout the area of the surface, right? So a surface is a two-dimensional object or a two-dimensional thing. So for any two-dimensional thing, the dimension that we need to be concerned about is its area. Okay, So let me represent that by A. Had it been a square, then that area would be represented by L square. If it's a triangle, that will be given by half base height, and so on. So the formula for the area would be depending on the figure and the shape and size of the object. Now here the letter that denotes the surface charge density is represented by sigma, and sigma is given by total charge upon the total area. Right? Just like linear charge density was given by charge upon its length, this surface charge density is given by charge upon the area. So if I consider a small section of that area, if I consider a very small section of this area, if that section is considered having area dA, and suppose dq amount of charge is spread over that area, then sigma can also be written as dq by dA. From here dq can be given as sigma into dA. In order to get the total charge, I can integrate both sides. So that is what is known as surface charge density. This is nothing but charges spreading over a particular surface evenly, or continuous charge distribution over a particular surface. If I need to know its unit and as well as its dimension, I can take it as the unit for sigma would be given by what? Coulomb per meter square. So that would be Coulomb per meter square, or we can also write it as Coulomb into meter to the power minus 2. Similarly, the dimension would be given by what? For charge, the dimension is again, it would be given by current into time. So that would be AT, and meter square, that would be L square. So this is nothing but AT L to the power minus 2. So that is the dimension for surface charge density. Now let us discuss the last type, which is known as volume charge density. So the last type of charge density that we are going to discuss is volume charge density. So volume charge density is for charges spreading over a particular volume. So for any kind of volume, we need a three-dimensional object. So let me take a cube like such. So if I spread some charges into the volume of this cube, let me give some charges Q into the volume of this cube such that that charge is spread all throughout this volume. Let me represent the volume of that cube by the letter V. So if that is a cube, then that particular volume would be given by L cube, where L is the length of the side. Had it been a cuboid, then that would be given by length into breadth into height, and so on for other volumetric figures. So for this kind of charge density, the letter that represent that density is given by or represented by rho. So rho is nothing but total charge spread over the total volume, that is V. Okay, now if I need to consider charges spreading over a small section of the volume, that is dV, then that charge would also be considered as dQ. So for any smaller section, the same rho can be represented as dQ by dV. From here I can write down the expression as dQ as rho times of dV. In order to get the total charge, I can again integrate it. So this expression represents volume charge density, which is nothing but charges spreading evenly or continuously over a perfect volume. So the unit for volume charge density is given by Coulomb per meter cube. I can also write it as Coulomb into meter to the power minus 3. Similarly, the dimension of volume charge density would be given by substituting the dimension for charge as well as for volume, that would be AT divided by L cube. So this is nothing but AT L to the power minus 3. So that is the dimension for volume charge density. So these are the three types of charge densities that we will be taking use of in our further explanations. Thank you.